You're continuing your brilliant career in calculus by now learning some new integration techniques. You see these three in the red, those are the ones we're headed to. These are the ones that you've already covered in your calculus life, and not in this course, but in some future calculus course, you are probably going to cover this thing called trigonometric substitution. Before we get going on this, I have a statement. It's a universal truth. You should take this statement seriously. That is a true statement. So do with that what you will. As we go through these new integration techniques that you see right here, they will rely on some of this stuff from the past for sure. And also available to you on the lesson plans is a note packet that's really good for information and really good for practice. I believe it's filled out on the lesson plans as well, so that you know that there's some correct answers. So I'll be referring to that as we go through here. The focus of today is going to be the integration by parts, and you see down here it says tabular. That's going to be a little trick to help you with integration by parts, but it doesn't work all the time, so we're not going to cover it on the very first video. Okay, here we go. Integration by parts requires that you memorize this clunky formula. And you say, what? I don't want to memorize that. But it's not going to be that bad. First of all, it says basically if I need to do an integral of something, and it turns out I decide I need to do integration by parts, I need to use this formula, uv minus the integral of v du. Well, it's not going to be bad to memorize because think about this. Don't you want to go on a vacation to the Caribbean? Yeah, it would be so nice because you could sit in the beach and soak up the sun. But wait, there's voodoo in the Caribbean. You don't want the voodoo, right? Well, use that idea to help you out. You want the sun, UV, minus the voodoo. So UV minus the V du. I want the sunlight minus the voodoo. Or if you don't like that, just memorize it on your own. Okay, so the very first problem we're going to work on is from these note packets, and it's this bottom one, integral of x times cosine of x. And this one is about as tame as they get. So there's that problem, and you know, when you're presented with an integral problem, you're going to have this dilemma. You look at that and say, should I be able to do this by hand? Meaning, can I do this antiderivative just by raw brain power? Well, it turns out I don't think you can. Maybe there's a few freaks out there like you who can, but most people cannot. So if I can't do that, one of the next things I always thought about was Usubstitution. Can I pick something out of here to become my u so that it has a derivative that cancels out another part of that integrand? That's the key to Usubstitution, and again, that answer is no. So if you've exhausted those two ideas, you're probably going to then choose integration by parts. And by the way, integration by parts you'll often recognize because it applies when usually one thing is multiplied by another thing, but it doesn't always have to be that way. And you should also know that we are not going to do integration by parts with fractions. And I'll talk about that in a little tip at the end. All right, so let's just get going with this problem. So what I would do, hold on here a second. As I go through this problem, I'm going to be following these steps. I've identified that it's going to be integration by parts, and I've memorized that formula. Now none of this stuff makes sense to you yet, but if you either copy this down or wait till we do an example or two and decide whether you want to come back and copy this down, that's up to you. But this is the framework that I'm going to be using, so you have that available to you. Okay, so that framework said, once I've decided that I'm going to do integration by parts, I need to build a table for myself. And this is kind of like your first step in Usubstitution, where you would look at the integrand and select a u and then do some derivative gymnastics. We look at this thing and we select part of the integrand to become u and part of the integrand to become dv. So I make this u selection and this dv selection, and then conveniently right below it I say u would have a derivative du and dv would have an antiderivative v. So if you remember u and dv at the top, what goes below it is either the derivative or the antiderivative. Now I selected x, and I'm going to explain more about y later. And then that leaves, if I select x for this, that leaves actually cosine of x dx for the dv. At that point I would say, all right, if I selected this for my x, and that is my u, what is the du? You might say 1, and you're right, but it's really 1, and then, let's see, 1 dx, because I just took the derivative of an x term. And if I do the antiderivative here, it's sine of x, and you could write the plus c there if you want. If you don't do that, and I normally don't because it's going to show up later anyway. All right, I mysteriously selected these two. I did their derivative and their antiderivative. Once I've done that, I should have enough information to populate this formula. So that's exactly what's going to happen on this next step. Where I see a u and a v, I just replace it with the u and the v. Where I see an integral of v, that's the integral of sine of x. And where I see a du, I write the dx. So be careful, because a lot of times people, never mind, you'll figure it out when you practice. All right, so I've populated that formula, and now I'm sitting there like this. That's not really my final answer, because you'll notice that this part right here is in integral form, and once you've done this table, once you've completed this table and you've filled in the information, the last step is continue on with any applicable integration technique. Remember, you know a lot of integration techniques. So this spot right here, you still have to do integration. Hopefully it's something very reasonable, and in this case it is. You know the antiderivative of sine of x very, very easily. You have to be super careful because there's some negatives floating around. But the antiderivative of sine is negative cosine. That negative was still there. This ends up being my final answer. Notice when I did that antiderivative, I remembered to do the plus c. And let's see here. This is my final answer. So what that's saying is this is the antiderivative of that. Since there were no limits of integration, I don't end with a number answer, I end with an antiderivative answer. If there's limits of integration, we'll talk about that in a little bit. Okay, so you might be skeptical. You might say, I'm not really sure that's the antiderivative of that. Thank you for being skeptical. I have taken that. That was our answer. And if that's my antiderivative, I can go ahead and take its derivative to see if I end up back with the original problem. And by doing product rule, and let's see. Hold on one second here. I missed something. Okay, I have it back. So that was my answer to that problem. If I take its derivative, I should end up at the original problem. And by doing product rule and doing that derivative, these two terms add to 0. That leaves me just with that term, which, by the way, was the original problem. So that means I know I've done that problem correctly. All right, so to recap, I memorized the formula. I recognize that this is an integration by parts situation, and if I do that, I carefully select a u and a dv, so I can find a du and a v, and this information plugged into here gives me a workable problem but I still have to do integration on this part no matter what, and that's that. So you should be asking, how did I know that was going to be my u and that was going to be my dv? Well, there's some tips, but it's still a little bit like Usubstitution where it's educated trial and error. But here's a list of ideas for your brain. First of all, the u should be something that's easy to differentiate, which makes sense because in your formula that you're using, whatever you select for u, you have to, right below it, write its derivative. So you should pick out something good for u that has an easy integral. Likewise, your dv should be something reasonable to do an antiderivative of because you're going to turn your dv into a v in that table up above. And just a reminder from something before, if your original problem is in fractional form, that's not going to work for our integration by parts. So what you would do is do an eyeball adjustment and turn it into a form that would work for our integration by parts. So the problem we just worked on was number 1 in the notes. Number 2 in the notes, I'm going to do a quick 2-minute video on that here and make that separate. But number 3 in the notes would go ahead and continue on with what we did in number 1. This is kind of a rare case, but it can happen. In this original problem, I identified that I wanted to do integration by parts, and so I got to this step. And like I had mentioned earlier, when you get to filling in the formula, that integral, I've said that you need to continue on with what you know about integration. Well, unfortunately, if that's not something you can do by hand or by Usubstitution, you may have to do integration by parts a second round. So because I couldn't do that antiderivative, I did a second round of integration by parts. So as you look at number 3 in the notes, you should study this problem and see what the heck is going on there. We're going to have a possible aid to this sort of pain and agony, but it's still also a possibility that the AP gives you a problem like this. This is our intro to integration by parts. I highly recommend that you're looking at the notes packet, especially number 1 and number 3 right now for practice. And then there's going to be 2 much shorter follow-up videos to show you some more nuances of integration by parts. See ya.